So it's 3:30. We're not so late. The idea now is to talk about the DNP mechanisms. But before I talk about the DNP mechanisms, I will have to first introduce some basic properties of the sample, because that's where the DNP takes place. I will have to present some important properties of the electron spins, the EPR line shape, the relaxation, etc. Some important properties of the nuclear spins. And with all this, we can then start to talk about DNP mechanisms. So today we won't talk about DNP mechanisms. We'll start with the sample and the electrons. And I think we'll leave the nuclear spins and the DNP mechanisms for tomorrow. So DNP sample. Okay, so DNP, dissolution DNP is a one-shot experiment. So the game is to build up the polarization as high as possible because it will only be used for once, okay? So we go in conditions where the electron polarization is as high as possible. Usually we try to aim for 99 point something %. So initially the dissolution DNP was done at 1 Kelvin and 3 Tesla, where the electron polarization is 95%. The proton polarization is 0.28 and the carbon is 0.072%. So in a typical DNP sample, we have 30 to 90 millimolar of radicals, typically. This is 2 to 6 10 to the 19 per cubic centimeter. I just put this number because a lot of the literature in physics use this notation. So 2 10 to the 19 spins per cubic centimeter is 30 millimolar. There are many reasons why this is a kind of sweet spot. If you go below, if you go higher, the DNP usually works less. It's slower or it's lower. The many reasons are related to the coupling of the electrons between them, the spectral diffusion. So how does the irradiation perturb the EPR line, the nuclear spin relaxation, and others. So there are many, many reasons why there is this sweet spot for DNP, for dissolution DNP, which is on the tens of millimolar range. The molecules that we want to polarize, usually we put them at the highest concentration we can. And the solvent is usually partly deuterated, and it has some glassing properties. And this is for having a statistical distribution of the radicals. When we freeze, we want a glass, as we said. And also we deuterate because we want to reduce the content of protons. Okay, we notice that if there are less protons, usually the protons polarize higher or faster. And we will talk about that in more detail in the DNP section. So usually the DNP juice, for example, in MAS DNP only has 10% of water. The rest is deuterated. And this is enough to do CP. We don't need a fully protonated sample to do efficient CP. So the DNP goes like this. You have your electrons that are dispersed in your sample. You cool down. Hopefully it forms a glass. You shine microwave and you polarization. You transfer polarization to the nearby nuclear spins. And then, that's the basic picture we have in mind. We have nuclear spin diffusion that transports the polarization all over the sample, over nanometer distances or even micron. That's the very basic picture. So in this sample, you have a solvent, you have radicals, you have your molecules of interest. So you have many magnetic interactions that are going on. I'm not going to enter into the detail of the equations of the Hamiltonian. I just want to summarize things here. You have the electron Zeeman interaction, which is the interaction of the electron with the magnetic field. Usually this amounts to several hundreds of gigahertz. So in our condition, it's 200 gigahertz. So it's a lot of energy. Okay, this term contains a lot of energy. Electron zero field interaction and exchange interaction, we will not talk about it because it's only for very, very proximate electrons. It's for highly concentrated or for biradicals. Electron dipolar interactions, this is an interaction that is also important for us. Usually the electron-electron dipolar interaction is on the order of several tens of kilohertz, hundreds of kilohertz, or even megahertz. Okay, so it's much less than the Zeeman interaction. You can have electron nuclear hyperfine interactions. So that's interaction between the electron and the nuclear spins of the radical. So it's the nuclear spins where the density of the electron is not zero. So and then you have electron nuclear dipolar interaction through space, which is also very important, but very small in terms of energy. Nuclear Zeeman interactions, which is also very small compared to the electron. It's only a few tens or hundreds of megahertz. And for some nuclear spin, but we'll not talk about it, you have nuclear quadrupolar interaction. And another interaction that is very important is the nuclear-nuclear dipolar interaction that can transport polarization, so enable spin diffusion. So you have all these interactions, and we can already make some separations and think of them in terms of how much energy do they represent. So there are terms that are high in energy: Zeeman interaction, electron dipolar, electron nuclear hyperfine, nuclear Zeeman interaction. These are on the order of megahertz to gigahertz, and terms that can be neglected from the point of view of energy. In our sample, because in our sample, we neglect the zero field, the exchange, and the quadrupolar because we only pay attention to the spins 1/2, and we assume that the radicals are statistically distributed and are not too proximate. But there are other terms that are very small in terms of energy, but are super important. So there's the electron nuclear dipolar interactions, which enables the transfer of polarization from the electron to the nuclear spins, because it has not only diagonal terms, but cross terms that connect the electron to the nuclear spin. So even though these interactions are on the kilohertz scale, they are the terms that drive the transition and that enable polarization transfer, even though they don't have a big impact on the energy of the system. They are like the vehicle for transfer. Then there is the nuclear-nuclear interaction. Again, the couplings are a few hundreds of hertz or kilohertz. So it's very small in terms of energy, but they connect the nuclear spins between them. And again, this dipolar interaction is the vehicle for polarization transfer from a nuclear spin to the other one. So it's what enables spin diffusion. So in the course, sometimes we'll make some energy calculation. We'll make some energy conservation calculation, and we will neglect some of these terms because they are super low in energy. But it doesn't mean that they don't do something. They're super important, but they can be neglected in the calculation of the energy, okay? So first, let's look at the electron spin. So as we said, for the electron spins, we want to consider Zeeman interaction, dipolar interactions, hyperfine coupling. And we will also consider of course, the J anisotropy of the Zeeman interaction. This is the spectrum of a tempo at 5 Tesla, and this is the spectrum of another radical, BDPA. You see the tempo is very broad, whereas the BDPA is very narrow. It's a bit like the trityl radical that I mentioned before. So why do these radicals have so different line shape? And this is very important for the DNP. It will determine the kind of DNP effect that we have. So we have to understand where does the line shape come from. So I will go through these different interactions and see the impact that it has on the line shape. I will not go through the calculation, okay? This is really not the goal here. The goal is that you have an intuitive view of what's going on, that you understand without knowing the equation, and then I will give you the links to the papers and the books where you can find the equations if you want to go further, okay? So first we have electron-nuclear hyperfine coupling. For example, for tempo, we have the interaction between the electron and the nitrogen 14, because the electron sits on the nitrogen oxygen bond. So there is a strong hyperfine interaction between the electron and the nitrogen 14. This interaction is anisotropic. So it has three values that are defined in the principal axis of the molecule. That means that depending on the orientation of the molecule with respect to the magnetic field, this hyperfine coupling changes in value. It ranges from 20 mega to 100, from 10 mega to 100 megahertz. Okay. So now if you have a tempo molecule, a nitroxide molecule that is maybe like as a crystal, imagine everything is aligned. What you would see is three peaks which arise from the coupling with the nitrogen 14, which is a spin 1. It has three states, the nuclear spin, so you have three lines. This is in one axis, this is in one axis, and this is in the other axis. So you see the splitting changes a lot in amplitude. This is if you have a crystal, but in reality we have a powder, a glass. So you have all the orientations. And that gives rise to a broadening. So we have all the possible combinations of orientations, and this gives rise to a broadening. On top of that, we have the Zeeman interaction. So this is interaction between the spin, electron spin, and the magnetic field. And again, this is anisotropic. So depending on the direction of the molecule with respect to the field, it has different values. So altogether, if you are in a glass with hyperfine coupling that is anisotropic and J anisotropy, so anisotropy of the Zeeman interaction, you end up with this kind of patato for temple. And you can guess the features here. You can see some hyperfine coupling, and on top of that you have the J anisotropy. So this is a simulated spectrum for temple at 3 Tesla, 3.35 Tesla, with all the possible orientations, which is quite close to what we have in reality. So each frequency corresponds to certain spins that have the right orientation. So if you irradiate somewhere, you will only hit a few spins that have the exact perfect orientation, and that sit at this frequency. Now, on top of that, we have dipolar couplings. But before talking about dipolar coupling, I just want to give you a definition. So in EPR, we often talk about the inhomogeneous line. Okay, inhomogeneous line means the EPR line that arises from this hyperfine coupling and this J anisotropy. Okay, it's the broadening of the EPR line through these interactions that is called the inhomogeneous line. And we can call, for example, F omega the line shape of the EPR spectrum. So F would be the intensity as a function of the angular frequency. And we will use this F omega in the course in a way that is normalized. So we say that the integral of the EPR line is equal to 1. Okay. Then you can define the center of the line. The problem is the line is not a Gaussian, it's a patato, so you have to measure the center of gravity. And so in the course, we'll use this omega 0, which is the center of gravity, the integral of omega times F omega. And then we can define the second moment, which is the integral of the delta omega square with respect to the center of gravity times the intensity. This gives you basically the square of the width of the line. Even though the line is not well-defined shape, you can get a number out of it, which is the width. Okay? So if you take the square root of this, you get a width. So for tempo at 3 Tesla, the M2 is 11 megahertz square, 11,000 megahertz square, and this gives 340 megahertz width. There must be a mistake somewhere. There's a 0 missing here. Yeah, sorry. Thanks for noticing. And that's about what we saw on the spectrum before. So 300 megahertz width at 3 Tesla. And the proton line width is 150 megahertz. But that's not all. So we have electrons, and as I said, the concentration is very important. This line shape would be true if the electrons are super dispersed, so super low concentration, no interactions between the electrons. But in reality, the electrons are pretty close, a few nanometer, so you have dipole-dipole coupling between the electrons. Okay, and this has a strange formula that also depends on the orientation of the vector between the two spins and the magnetic field. So depending on the orientation of the two spins with respect to the magnetic field, the value of the dipolar coupling changes. In front of this scalar vector, you have this term here that gives the strength of this dipolar coupling. And for example, if you have two electrons that are separated by 1 nanometer, it will be about 50 megahertz. And it goes with the cube of the distance, 1 over the cube of the distance. So the further away they are, the smaller it gets, and the closer they are, the higher it gets, this dipolar coupling. So if you have an arrow line like that, and you bring some electrons nearby, and you put that in a glass at high concentration, you will broaden the line. So the line gets broadened by all these dipolar interactions. So in reality, the lines that we have, it looks more like this. You see, before we had all the nice features that would appear, and now we have a even more potato-like shape. Okay, so you can calculate the width of the dipolar broadening, and then you can apply this broadening to the line, and you get something closer to what you see. The typical broadening is, for example, for 15 millimolar, it's going to be 0.2 megahertz. For 60 millimolar, it's going to be closer to 1 megahertz broadening. Then there is a term here, which is 1 minus p square. I'm not going to explain it in detail now. It's going to come back many times in the course. If all the electrons gets polarized, this broadening goes down to 0. The more electron polarization you have, the less disorder you have in your sample on the orientation of the spins, and the narrower the line gets. Of course, when we do DNP, we shine microwave, so we killed some of the electron polarization. But that's just to give you an idea. So we have a line that is like 300 megahertz width, but the dipolar couplings are only 1 megahertz or less. So that's why the main features of the line, they remain, but it's somehow a little bit broadened. So the little details go away. If you get too much concentration, the dipolar coupling gets super high and your line gets too broad and the DNP doesn't work efficiently. But if you don't have enough radical concentration, you don't have this dipolar coupling. And it turns out that they are super important. We'll see in tomorrow how important this dipolar coupling is. Another important parameter of the electron is the relaxation. So the literature on relaxation of electron is really difficult. I really don't understand much about it. But it seems that there is a general agreement in the literature by the Abraham, Goldman, even today Vaneeckhaute, that the process that dominates below 4 Kelvin, so in our conditions at 3 to 7 Tesla, is called the direct process. The direct process is an exchange of energy between the electron and a quantum of lattice energy, which is called a phonon. So it's like vibration of the lattice of the sample, modes of vibration that gives energy to the electron and that make the electron relax. Okay. In our condition, the electron spin lattice relaxation in the direct process is proportional to this, to omega to the power 5 times the cotangent hyperbolic of h bar omega over 2 kt. Okay. There are other mechanisms that can happen, but usually they happen at higher temperature, more than 4 Kelvin. It's like the Raman process or the Horbach process. This involves several phonons. So the Raman is 2 phonons exchange energy with 1 electron. There are very, very few measurements of electron relaxation in our conditions. I don't know, I found 2, maybe there are 3 or 4. It's really hard to find people who measure T1 of electron at 1 Kelvin and at 3 to 7 Tesla. One paper is from Kochenberger. They measured the relaxation of temple at 1.5 Kelvin and 3 Tesla, and they got 0.3 seconds. Okay, they did that with longitudinally detected EPR, 0.3 seconds. We did it also, and we measured, I think it was closer to 1 second when we did it at 3 Tesla. Then we measured it at 6.7 Tesla and 1.2 Kelvin, and here it was 50 milliseconds. So we see that if you go higher in field, it gets shorter. If you do the calculation, it's not quite correct. We miss a factor 2 or 3, but it seems like it goes in the right direction. And when we change the temperature from 1 to 4 Kelvin, it doesn't change much. So it seems to be close to this direct process. Yeah. Yeah. Diana?
No vibration there.
Yeah. I mean, 0 Kelvin is theoretically impossible, but that's probably the case. Yeah. Huh? What is? I don't remember. What is PL? I think this is the polarization of the electron. So this formula says that if the polarization goes to 1, you still have relaxation. So this. What? Really? Oh yeah. Okay. That's.
I don't know.
Yeah, maybe this direct process breaks down if you go sufficiently low in temperature. I don't know. This has been shown. Maybe Kelvin temperature, maybe.
Here you are talking only about temple or also other radicals?
The only reference I'm talking about are temple, but there are also a few references about tritium. Maybe 1 or 2. And tritium has also a T1, which is on the order of a fraction of a second. I think it's closer to 1 second. It's a bit longer than temple. But the main message here is, yeah, keep in mind these values. We are below a second, tens of milliseconds, hundreds of milliseconds in our conditions. That's the time it takes for the electron to relax. It's pretty long. But compared to, I mean, at room temperature, the T1s of the electrons are microseconds or less. Even at MAS DNP condition, the T1 of the electron is more like 100 microseconds at 100 Kelvin. So it's very, very long. So now there is a fundamental question in DNP. Before we do any transfer of polarization, that we should ask ourselves is what happened when we shine microwave on the EPR line? And there are many ways to see what's happening, and there was a lot of debate in the community about that, even between Goldman and Abraham, and so there was a lot of debate. So imagine you have a very narrow line, and you shine microwave with a B1 which is broader than the line. You could imagine that after a while you will just saturate the EPR line. You will equalize the population of spin on the energy levels, and therefore you won't have any EPR spectrum to observe anymore. You will destroy the whole line, the polarization of all the spins. Of course, that's not the case. We have a microwave field which is very weak. We have a line which is very, very broad. This is impossible in our conditions to achieve. We have J anisotropy, hyperfine coupling, dipolar coupling. So at the end, we have a line that is super broad. And so the fundamental question is what happened? What happened when you shine microwave? Does it completely saturate the line? Does it propagate? How does it propagate? What will be the shape of the EPR line under saturation? And this is really, really important. So if you have a B1 of, say, a few kilohertz, that's what we have. We have a microwave B1 of a few kilohertz. So we only saturate a tiny portion of the EPR line. Well, the first thing we can imagine is that spectral diffusion can transport this saturation to other spins through dipolar coupling. So if you saturate one spin and it's coupled to another one that has a nearby frequency, it can flip-flop and exchange the energy. And then you have a kind of diffusion, but we call it spectral diffusion because we see it spectrally diffuse. We see the diffusion on the spectrum. If the spins have two different frequencies, they cannot really flip. It's not energy conservative, but if they are close enough, if the shift is smaller than the dipolar coupling, it will be very efficient. They can flip-flop. They can exchange energy spontaneously at a rate which is equal to the dipolar coupling. And the dipolar coupling is 1 megahertz. So that means in 1 microsecond, the spin exchange energy with the neighbor. So the more coupling you have, the more concentration you have, the more the saturation is going to diffuse. And here you can see the plot of the EPR line for different diffusion constant that can be calculated. If you want to have a look, Vaneeckhaute book on page 79 to 91. It's this book, and I really highly recommend that you have a look at it. Yeah, it's there's really a lot to learn from the book. So these are for arbitrary diffusion constant that were calculated for very, very small dipolar coupling. In reality, in our samples, if we calculate the diffusion constant for 30 millimolar concentration, and I did not do it, Vaneeckhaute did it, so we have to trust him, it's 0.58 10 to the 22 second minus 3. And if you calculate the time it takes to diffuse through the whole line with a line of 300 megahertz, it's about 17 microseconds. So if you shine microwave somewhere in the polarizer on your EPR line, it should take about 17 microseconds to propagate. That's a typical time constant. It's super fast. If you compare it to T1, T1 is what, 50 milliseconds? So there are 3 orders of magnitude. It's at least 1,000 times faster for the saturation to propagate than the relaxation. And this is really the central important point in the DNP process. This will dictate the kind of DNP that happens. Is spin diffusion faster than relaxation? It will have a huge impact, we will see, on the DNP mechanism. But we'll see that tomorrow. Yeah.
Does it break down if you calculate this and assume that neighbors that are very close and with different frequencies, maybe it breaks down at lower concentrations?
Yes, absolutely. Yeah, if you lower the concentration, the diffusion constant will go down, and the time for diffusion over the whole line will go up. So you will reach a point where the saturation will not propagate anymore. Yeah, and that's probably why we work with 50 millimolar, because we need this spectral diffusion to be fast. It's not there's a good reason for that. So you shine microwave, it propagates over the whole line. So what I showed before is totally wrong. In reality, if you shine microwave, it will just affect the whole line. And you could think, okay, killed the whole electron polarization. But if it kills the whole electron polarization, there's no DNP anymore. So there must be something happening. Okay? So I'm showing a bit the same as before. So imagine you have a crystal of nitroxides. You would have a super narrow line. But you have J anisotropy and hyperfine coupling, and you are in a glass. So you have all these electrons that have different orientations, and each orientation gives rise to a different frequency. So each frequency here corresponds to one specific orientation of the radical. And then, because we are at 50 millimolar or so, we have dipolar couplings. So these are coupled together, and we have a broadening of the spectrum. And most importantly, we have spectral spin diffusion that is activated. So when we shine microwave, it not only affects the electrons that are at the specific frequency, it must affect all of them. 1,000 times faster than T1. So this is our tempo line with an inhomogeneous broadening of several hundreds of megahertz. This is represented in terms of energy level. In reality, we don't have two energy levels, we have many energy levels because we have this broadening due to the anisotropy of the hyperfine coupling and the J tensor. So you can have a spin up or spin down, and you can have the spin on many different energy levels depending on their orientation. And the distribution of the population on these little lines of energy at thermal equilibrium is dictated by Boltzmann equilibrium. So it follows the exponential law. That means that there is some polarization gradient that is built in not only for spin up and spin down, but also within the broadening of the EPR line. So at higher frequency, the polarization is higher than at lower frequency. So some electron spins that have the right orientation have a higher polarization than other spins that have a lower frequency. So there is a small gradient of polarization here in the line. And this is, again, super important. It will come back when we talk about DNP, this gradient of polarization in the line. Now, we shine microwave. And if you don't consider fast spectral diffusion, what you do is you saturate the spins. It can propagate a little bit if you have a bit of spectral diffusion, but not too much. And that's what people call dig a hole. So you will hear that in the EPR community. You dig a hole in the EPR line. You saturate some of the spins, but not the other ones. So in terms of energy level, this means that some of the spins are saturated, and so for those spins you equalize the population, spin up and spin down. But for the other ones, they're not affected. Okay? That's not what's going on for us. Because we have what we call homogeneous broadening. We have dipolar couplings between the spins. So these packets of spin, they talk to the neighbors, and so it diffuses through the line. Okay. So I wrote 0.2 megahertz per millimolar, and then I read Vaneeckhaute book, and it gets another number. It's more like I miss a zero. I don't know who's wrong or who's right. I did this calculation 10 years ago, so I don't want to do it again. But anyway, we have let's say, on the order of a megahertz broadening in our conditions. So we have a homogeneous line so that when we shine microwave, the perturbation, the saturation actually propagates. That's all we know. It's going to propagate, and it's going to fight against T1. Because while it propagates, the T1, the thermal relaxation, the Boltzmann relaxation, wants to bring those spins to the Boltzmann equilibrium. So there's a competition between spectral diffusion and T1. But again, if I take the numbers, we have a spectral diffusion in 10 microseconds, and we have a T1 of 50 milliseconds. So T1 cannot compete against spectral diffusion. The spectral diffusion will be way, way faster in our condition. Again, it's in our condition. It's not in MAS DNP. So this is something we'll talk about during the DNP session tomorrow morning, is this competition between spectral diffusion and T1, and what will be the shape of the EPR line, because only when we know the shape of the EPR line, we can know the enhancement. We can know how it will transfer polarization to the nuclear spins. Okay, now, okay, what happens if spectral spin diffusion is very, very efficient, like in our case? This was a huge debate between Goldman and Abraham. And actually, Goldman came up with a theory of thermal mixing and dynamic culling, which was based on previous work from mainly Redfield and Provotorov. Provotorov developed, it was in the early 60s, the theory of saturation of magnetic resonance lines, EPR and NMR, under strong coupling condition. Okay, it was a paper that was published in 62, I think, in Russian. And at that time, in France, Abraham, who was speaking Russian, he was from Russian origin, but he was living in Paris, in France. He met Provotorov at a conference in Russia, and Provotorov came to him with this manuscript in Russian. And so Abraham could read the manuscript, and then he could, with the help of Goldman, use this theory to understand what's the line shape looking when you saturate and how's the DNP going, and then they published that. And later, the Provotorov paper was published also in English. It was translated in English. So if you look at the first papers from Abraham and Goldman, and they're citing this paper from Provotorov that nobody can read except Ekaterina, but now you can find the translation. And what is really nice with these journals in Russia is you click here on the link and you get the paper. You don't need any access. It's all free. So you can get access to all the translated papers in English. And what this paper describes is totally counterintuitive. And I don't really understand. I don't know the theory behind. I don't understand why. But what it says is that if you have a very fast spectral diffusion and you shine microwave somewhere, you will not saturate the whole line. The spins will redistribute in a way that can be described by a temperature. So the spins will reorganize and will follow an exponential law with a temperature that can be calculated. We will calculate the temperature by using some energy conservation law, very simple thermodynamical law. But there is a new temperature in the frame of the microwaves. So it is as if you have removed the microwave frequency, you go in the frame of your microwave, you look at the spectrum, and you see a new distribution of population that is described by a spin temperature. It's really hard to believe, and I mean, from what I've heard, between Goldman and Abraham, there was really some big debates. So Goldman took the idea and was really in favor of it, but Abraham was very against it at the beginning, the idea of thermal mixing, and so it took a while before this theory was accepted. The nice thing is that some people tried to demonstrate that experimentally, and they did. So instead of having a full saturation, you have this very strange shape with a negative lobe. So it's like you create negative polarization and positive. So the total is 0, but like some spins go up, some spins go down depending on the frequency. And this can be experimentally observed. It was observed in 69 by Vaneeckhaute. I don't know what system is that, but he would shine microwave and then he would record the EPR spectrum rapidly and he would see this very strange shape. And it was also demonstrated in Russia by Atsarkin. I don't know what system is that, calcium fluorine, some paramagnetic center. And again, you would see here the normal line, and when you shine microwave, you would see this very strange shape. It was also demonstrated a bit later by Atsarkin in other systems I don't know, cesium 3+ in I don't know what. Again, you see this strange line shape here. It was also demonstrated in NMR lines. So if you dig in the literature, you see that in NMR as well. Yes? I don't know. I have to admit I didn't read the paper. I copied the reference from some books and copied the figure. I read the Provotorov paper once, but not this one. Yeah. So this, I will not go into detail. I will not explain why there is a temperature that pop up. Why? Because I don't understand. I mean, I tried to look at some papers. There are some papers where they demonstrate that with thermodynamic, with statistical physics. There are some papers that demonstrate that with full quantum simulations with many spins, and this has been done since then, but very recently. It's like in the year 2016 and 2018. There's a group in Paris. It's Alberto Rosso, who does some statistical physics, and he has done this simulation on a many spin system. And he got this also demonstration of the existence of the spin temperature in the rotating frame, in the microwave frame. There's also a demonstration by Shimon Vega. At the beginning, he was strongly against it. In the first conferences, he was saying, this is rubbish. You have to go to the real quantum mechanics and do the calculation. And if you see all the papers during his life, he gets closer and closer to the idea that, yeah, maybe. So he was working on the full simulation on, I don't know, it's not many spins, it's maybe 11 spins or so, because it's hard to simulate a lot of spins. And you need a lot of spin because this is really a collective effect. But he managed to get this line shape without any assumption, just full quantum mechanical simulation on 11 spins. Okay, so there are a lot of considerations that are thermodynamic, like related to entropy, but I don't remember what is really entropy. But they say that if you shine microwave, the electron will distribute their population in a way that will, I don't know, maximize the entropy of the system with respect to the perturbation. So I'm sorry, this is really hard. I tried to dig in the books. I thought maybe in the Vaneeckhaute book I will find some good explanation. It's one line in the book. It just says, Provotorov, spin temperature, just trust me. There's no formal demonstration. But if you feel like you can, and I can't, dig in these two papers and maybe you find a good answer that convinces you. So the way I'm going to convince you is not through theory, but it's through experiments. We'll show you some very strange effects that only happen in this particular case of spin temperature theory. Okay. So you have your electron spins that have different energy levels that are distributed at thermal equilibrium with a very high electron polarization. So this is spin down and spin up have a huge difference in population. There is a small gradient here because this is hundreds of megahertz, so we have a small gradient of polarization. And then you apply microwave, and what spin temperature theory or saturation theory from Provotorov says that instead of having a hole, digging a hole, you saturate the spins right at the frequency here, but then you create this very strange dispersive shape in the EPR spectrum. This means that you will reorganize the spins according to an exponential law, a spin temperature in the rotating frame. So you saturate and the spins go like this. And so Provotorov paper is really hard. If you want to I think the thing you need to read if you're interested in this is the Abraham and Goldman paper from '78. It's also available online free, so Progress in Magnetic Resonance. Yeah. So the important question that we raised are the following. How broad is the line? Why is the line broad? Is it homogeneous or inhomogeneous? Do we have dipolar couplings that make the line inhomogeneous and that make spectral diffusion efficient? And in our case, I hope I convinced you that it is the case. We have a long T1, we have a short spectral diffusion because we have megahertz couplings, and so we have fast spectral diffusion. And in summary, can we dig a hole? In our case, no. In principle, we cannot dig a hole. We will perturb all the spins. Huh? Yeah, I just want to check if people are alive online. Are you here? They all went. They all left. Oh, no, Luan is here. Fatima is here. Emma is here. Lydia. Ah. Thank you for coming back. So I think it was really fast. There was no many questions, and that was my plan for today. We could make a small break and continue a bit. Yes. Yes. So please, if you have questions, we can answer question now, have a small break, and then continue with nuclear spins. And I think we will finish with nuclear spins. It will take maybe half an hour. So we will end at 5, I think. We have a 10-minute break after the questions, and we finish with nuclear spins.
I have a question.
Yes.
I can. So you say that in this case the spectral diffusion is faster than the relaxation, but it's not the case for MAS and MR. And you, in this case, can you explain? Because I'm not familiar also with MAS, DNP.
So in MAS, it's much more complicated because the sample spins. But let's say if you are at 100 Kelvin and you don't spin, you have a spectral diffusion that is on the order of, 17 microsecond for 30 millimolar. And you have an electron T1 that is 100 microsecond. So yeah, we are really at the border, at the limit. So probably in the MAS DNP regime, at 100 Kelvin, you could dig a hole that is quite broad compared to the EPR line. And all the indication of the DNP that is observed under MAS does not support the idea that there is a spin temperature. I will show you then a lot of different experiments that show that there is a spin temperature, and under DNP MAS they don't see these effects. So it seems like the situation is very different. Most of the theory that is developed by Vega or I don't know Griffin and Fred Mentang-Vigier is all about like digging a hole and yeah, there's the effect of spinning also that is super important, but it doesn't involve the spin temperature.
Maybe it's worth noting that the spectral diffusion does not depend on temperature or really little, while the T1 does a lot.
Yeah, the T1 does a lot. Yeah. And under MAS, they spin, so it's even more complicated because all the spins, the electron spin, they get different frequency during MAS rotation. And this rotation is also very important for DNP. It creates some additional effect that can lead to transfer of polarization between electron and nuclear spin. So it's much more complicated. And I'm really not familiar with that.
But in any case, it's not related to the fact that the sample is solid, because at the end, in this case, you use also glass, not liquid also. I don't know if you understand my question.
It's in solid. So in MAS DNP, they are at 100 Kelvin, so it's frozen or it's solid. For liquid, it's a whole different story.
I think there were questions here.
Any questions? Any question online? Yes.
So, okay, so with saturating the microwave, this also induces some heating of the system, right? Like temperature is increasing and maybe there is a compromise with the DNP polarization.
Yeah.
So the point is like, for instance, in my case, I have worked with glasses, and sometimes the effect of temperature increase is really like leveling out the polarization. I don't think that in the liquid DNP is like this. So
yeah. So we see that. If we increase the microwave too much, there can be a decrease in polarization because of the heating. We used to see that at 3 Tesla because we have a 400 milliwatt source. But now we have at 7 Tesla, we only have 80 milliwatt. We don't see that. No, we don't have enough power to see the decrease in polarization due to heating. But we see the heating. We can measure it in the helium bath. And this has an effect on the DNP for sure. What we don't know is the temperature of the sample. Because there's a huge helium bath, there's a sample that has some boundaries, and there is a resistance for the heat to go out, which is quite high at low temperature. There's this Kapitza resistance. So we can make some calculation. I don't think I showed the calculation, but I've done that in the past. And it shows that the sample heats quite substantially. And it's most probably, as you say, a limiting factor. So in the past, we used to make all our samples with little beads of 10 microliter because we thought that the polarization was better. And one day we became so lazy that we started to do ice blocks. But we never really quantified how worse it is, and maybe this is something. I think it's been 10 years. We're saying, one day we should do this experiment and compare, but we don't do it because it's so boring to do all these leads. But probably we might get better performance with beads than with block because of the heating problem. Maybe let's do that next week. There was another question. Okay, so we have a 10-minute break, and we start again at 4:35. So we'll have 25 minutes to finish the nuclear spin section, so that tomorrow we are only left with the DNP mechanism section. So we have plenty of time to finish the 130 slides. So yeah, we'll see. We'll go as far as we can tomorrow. But so little break, 10 minutes, and we come back for the next section.
Feel free to ask if you have a question that came up. Okay, if not, let's continue. So now we will look at the nuclear spin system and mainly talk about, again, the line shape of the nuclear line and the relaxation and the spin diffusion. So all the important things that matters for DNP. So in DNP, we're mainly concerned with C13 hyperpolarization. We'll also talk about proton NMR, but let's look, for example, here at the NMR line of C13 labeled acetate. So the C13MR line has a width of about, let's say it's about 10 kilohertz or something like that, 8 kilohertz, which comes partly from the chemical shift anisotropy. So the frequency depends on the orientation of the molecule. So there is an anisotropy, like the J anisotropy of the electron, but called chemical shift anisotropy, which is a few kilohertz. And there are some couplings, also dipolar couplings with the other carbon-13s and with the protons around. And the main source of dipolar broadening is the coupling, of course, with the protons that are nearby in the solvent and on the molecule. And so we observe for acetate a broadening that is typically on the order of 5 to 10 kilohertz, depending on the concentration of protons and on the temperature. Okay, but what's going to be really important for us is the coupling between the same spins, so carbon-carbon or proton-proton, because this is going to enable what we call spin diffusion. So it's going to help polarization spread over the sample. So the nuclear spin will exchange energy through this dipolar coupling, and the polarization will spread. So again, I will not go into any detailed equation or theory. I will just give you a simple-minded picture of what spin diffusion does in the sample. So our sample is a frozen glass with radicals and with our molecules. Some polarization will be transferred to the nuclear spins. We'll see how. And then nuclear spin diffusion will spread the polarization among all the nuclear spins. Okay, and this is really, really important for us, this nuclear spin diffusion process, because the polarization will not be transferred equally to all the nuclear spins. It will have a preference for the nuclear spins that are nearby the electrons, and then we will rely on spin diffusion to spread the polarization. So now imagine you have a line of nuclear spins, and by a magic trick, you manage to have some of the spins up and some of the spins down along this line. You do that instantaneously, and then you wait and see. And what spin diffusion is supposed to do at a rate which is on the order of the dipolar coupling, so kilohertz rate, it's supposed to redistribute the polarization in this line and make somehow the polarization homogeneous along the line. Now, if you have the same line of spins, and here you polarize the spins on this side, so you flip them so that they get always polarized in the same direction, and you keep doing it again, it's going to transfer to the rest of the line. Okay, so this spin is going to polarize, going to depolarize this one on, and then it's going to spread again. And so after a while, if you have efficient spin diffusion and you manage to polarize one spin on the edge, it should polarize all the line, given then that relaxation is not too fast. Okay. So what are the time scales for that? Where in our case, we have a diffusion constant for a protonated solid that is on the order of 10 to the 5 angstrom per square second. That's the typical value you find in the literature. That can vary by a factor 2, 3, or 4, but it's on the order. This is the diffusion constant. And then you can calculate the length of diffusion, which is the square root of d times the time. And if we take the diffusion time in 1 second, we find something that is about, the diffusion length is about 30 nanometer. It might be wrong by a factor 2 or 3, depending on the value that you find for the diffusion, but it's this kind of order of magnitude. If you let your sample evolve, spin diffusion will spread polarization over tens of nanometer distances within seconds. So it might seem slow. It takes seconds to diffuse on tens of nanometer time scale. But if you think about the distance between the electron, it's actually pretty fast. So the electrons are at a few nanometer distance in our sample, in our concentrations. So it's about 4 nanometer with 25 millimolar, again with an error of maybe a factor 2, depending on how you calculate it. But it means that within a second, the nuclear spin diffusion goes well beyond the inter-electron distance. So when we polarize, if the sample is homogeneous, if it's statistically distributed, we can assume that the polarization is more or less homogeneous because it spread much faster than it polarized. It takes 3 minutes or 10 minutes to polarize, but it only takes a second to diffuse between the electrons. Okay? So unless you have a very inhomogeneous sample with some particles or materials, if it's a frozen glass that is homogeneous, you can assume that the polarization is more or less homogeneous over the whole sample. So this nuclear spin diffusion goes from one spin to the other, from one molecule to the other. And everything goes well because, I mean, this spin has the same energy than this spin, plus or minus a few kilohertz. So they can exchange energy. They can exchange their polarization without any loss or need of energy. It's energy conservative process. So that's why it's easy, it's spontaneous. If you look at the dipolar Hamiltonian, it leads to a spontaneous transfer of polarization between the spins. And so if you write, for example, a 4 energy level with 2 spins, you see that there are 2 energy levels that are equivalent in energy. And so the spins can freely go from one energy level to the other. And this level are just spin up and down and down and up. So it's just an exchange of polarization between the spins, like on the line that I drew before. So this is going on spontaneously and pretty fast. Now there is a special case, which is the case where the nuclear spin is very close to the electron spin. So when you get very close to the electron spin, you have a dipolar coupling between the electron and the nuclear spins that shift the NMR frequency. And it can be several kilohertz, even several megahertz. If you get really close, it can get on the megahertz range. So it means that this spin here will have a significantly different energy transition than the other spin. And therefore, the transfer of polarization between the two spins is not energy conservative anymore. So if you look in the books and in my previous courses, you will see that I define a diffusion barrier here because I say, I mean, these spins are inequivalent, so you cannot diffuse closer to the electron than a certain distance. And it's defined in the literature as a diffusion barrier. It's a barrier. So what happens beyond this barrier is that diffusion is going fast, freely, whereas inside this barrier, we don't really know what's happening. We know that the diffusion gets slower because the energy difference gets bigger. We thought for a long time that it was a strict barrier, but there are many, many evidences in the literature that it's not a strict barrier. There are some probability that there is a transfer. So there is indeed a flow of polarization from inside the diffusion barrier to outside the diffusion barrier. But if you look in the Abraham book and Goldman book, they define the diffusion barrier and they say all what's happening inside doesn't matter. We don't see it, it's lost. And what really matters is the polarization at the surface here that then propagates. And this is fundamentally wrong. I mean, there is a flow of polarization from inside to outside, and there's a paper by Quentin here and us about observing this with some sequences. Paper from Bjorn, there's Corzelius, there are papers from Griffin, and many other papers that you cite in the paper that shows evidence that these spins that are very close, they are shifted in frequency. Sometimes you don't even see them by NMR, but they participate to the DNP process. Yeah, so Diana is asking if the barrier is spherical. It's not, because it's governed by the dipolar coupling, which has 1 minus cos square dependency, or 3 cos squared. So it has a very strange shape, like I don't know how do you describe this shape? It's yeah, a d orbital. So it's not spherical at all. You're right.
Just easier.
So yeah, it's approximated as spherical. They usually do a sphere, and you find values that ranges from 1 nanometer to, I say the 1.5, but there are paper where they say it's 4 nanometer, which is crazy. 4 nanometer is bigger than the distance between the radicals, so it means there would be nothing happening. So these nuclear spins that are really close to the electron, one thing we know is that they become invisible by NMR. They are so close that they're shifted in frequency, hundreds of megahertz, tens of megahertz. The lines get super broad, so we cannot really observe them. And that's something we observed in this paper, that the more radical you put, the less signal you have without DNP. So before you switch on the DNP, you see that part of the signal disappear in this sphere of influence of the electron, and we call them bleached or quenched. And as I said, so if you look at the paper from Quentin here on the diffusion barrier, it's called breaking through the diffusion barrier. We measure the exchange of polarization between these invisible spins and the visible spins. So when you have kilohertz couplings, you have pretty fast nuclear spin diffusion, tens of nanometer lengths over seconds, but it becomes slower near the electron. And this can be now quantified a bit more accurately with the sequences that was developed, the HIPRES sequence. But for now, in the rest of the course, we will just care about the bulk nuclear spin, the one that we see. And we will assume that spin diffusion is fast, okay? So we will assume that at any time, the polarization is the same for all the nuclear spin in the sample. Okay. One thing that is important is the relaxation of the nuclear spins. We want to fight against the relaxation. We want to polarize them. And in our condition, you can have direct electron nuclear spin relaxation. So it means one electron flops and induce some relaxation of the nuclear spins, which is not really relevant. We have another process that is much more efficient for relaxation, which is a 3-spin flip. Because the EPR line is so broad, there are many electron spins that can do a flip-flop very fast with the T2. And this induces relaxation of the nuclear spin. So you have exchange of energy between the 2 electrons and the nuclear spin. And I'm going to come back later on this 3-spin flip effect, because that's the DNP effect that we will consider. So it's the same effect that creates DNP and relaxation. What changes between the two is the distribution of polarization across the EPR line. If the difference of polarization between the 2 electrons is equal to the thermal polarization, then it creates a thermal polarization on the nuclear spins. Whereas if the two are very different, it can create a very different polarization on the nuclear spin. And this effect, this 3-spin flip process, which seems to be the dominant mechanism in our condition with a broad EPR line, according to Vaneeckhaute, is proportional to 1 over the T1 of the electron times the number of electron spins divided by the number of nuclear spins times d square, which is the width square of the EPR line, over omega 0 I, which is the nuclear Larmor frequency, times 1 over p square. P is the polarization of the electron. So the faster the electron T1, or in our case, it's not even a T1, it's a T2. Then the faster the nuclear spin relaxation. The more electron spins you have, the faster it is. The broader the line is, the faster it is. And there is this term that depends on the polarization of the electron. So if the polarization of the electron goes to 1, all the electrons are polarized. Then there's no flip-flop between the electrons. So the relaxation vanishes. And in our case, we see when the electrons are polarized, the relaxation can take hours for carbon. Actually, we don't measure relaxation at 1 Kelvin. We always go at 4 Kelvin so that the polarization of the electron goes down and there is some relaxation. Otherwise, it's just insane how long it is. Did we ever measure the carbon relaxation at 1 Kelvin? Or? Yeah. Yeah. Oh, yeah. Yeah. Yeah, yeah. So if it's an hour for proton, it according to the formula, it might be at least 16 hours for carbon, omega square. This is the rate. This is the rate. Okay, so we have very, very long T1. Unless the polarization of the electron goes down, then we have flip-flops, and that connects to the nuclear spins and creates relaxation. So I mean, I just wrote 2 important questions, but there are more than that. So is nuclear spin diffusion? In principle, yes, unless you have very, very dilute nuclear spins. We need to make the calculation, but for example, if you have only a few millimolar of carbon-13, then diffusion might be too slow. I know only one example in the literature where this problem arises. It was to polarize C13 in natural abundance on metabolomic sample with trityl. It seems that it was not working because of that, because there are so few molecules and at natural abundance that there's not enough spin diffusion to nicely spread the polarization on the sample. And that's why Gioiosa came to us, because he tried with trityl direct and he said, we couldn't manage to do it, so we have to do CP. Because then we have a lot of protons, we can polarize, and then we can do CP on the very low abundant carbon-13 spins. But in principle, for protons, we always have 10% of water. I mean, spin diffusion is super fast. So we will assume that spin diffusion is fast in the rest of the lecture. Bleaching, is it important? We saw on the figure that it's 10-20% of the spins that are invisible because of the electrons. So we will consider that this is not very important. We'll only care about the spins that we see, but this is not totally true. And especially if you have high electron concentration, you have higher and higher bleaching, less and less visible spins. So it becomes highly relevant. But for the sake of simplicity, we will make these 2 assumptions. One important thing is that the nuclear T1 is super long if you switch off the microwave. And so we're not really competing against nuclear T1. The DNP is going to be much faster than T1. Okay, question? So you mean, can we simulate that? Can we optimize the radicals concentration with a simulation? Yeah. Yeah. Yes. Yes, there is an optimum that we find experimentally, and tomorrow I hope I have time to go all the way to the derivation of the thermal mixing equation, and there, with the equation you can see the trend. So you can see if you move this in that direction, the concentration, the T1, you can see how it goes. But to really quantitatively find the optimum by simulation, I wouldn't know how to do it. I think it's hard enough to have the simulation that fits the data. But then once you fit the data, you can play with the parameters, and that's what we're going to try to do tomorrow, to look at the equation and see how the parameters affect the efficiency of the DNP. But I've not seen any papers where they can really quantitatively simulate and find the value. Because there are always parameters that you don't know. Like you don't know your B1, you don't know the exact distribution of radicals. I mean, it's really hard. It's really complicated. And the sample is so messy. Maybe it would be possible with full quantum simulation in a very simple system, a crystal with well-defined position, but in the glass, I don't think it exists. I don't know. Do you have any paper in mind where this has been done? Yes, we're happy when we can have the shape of the microwave spectrum. That's about what we can do. But yeah, if you increase radical concentration, it gets faster. If you have too much radicals, it degrades because your lines get too broad. If you don't have enough radicals, it's too slow. And you get out of the spin diffusion regime at one point and DNP collapse. So everything behaves as it should, but really qualitative.